So here we are in lesson 7 of unit 1. We're going to talk about continuity. This is our last lesson actually for this unit. So we talk about it being a function being continuous at a certain point. This would mean, of course, that we're going through without any breaks. We don't have any not continuous points or discontinuities in our graph. We can look at graph A, where we can see, even knowing we've got it restricted, our domain, we have no breaks. We're just traveling up and down a line or a curve. Points of discontinuity, common ones, are holes, which you see in part B there. We can also be discontinuous if we have jumps, as in part C. And of course, any vertical asymptotes, of course, would obviously get us a discontinuity. So those are the things that we're looking for. And so what we do is we say that a function f of x is continuous at any point A. 1, that point must be defined. And 2, the right and left hand limits must equal that function value. So what we expect to get is actually what the function is defined at. So, what does that really mean? So let's take a look at example 1 here. We have a nice little piecewise function, g of x, and we're going to look at what happens when we have these two values. Is the function continuous? Now, if it would be really nice if this was a polynomial function, of course, because we have nice polynomial functions are always continuous. But so we're looking at some other functions. And so let's look at this function, and what we're going to do, of course, is graph our two parts and then put it all together. So if we think about this, we've got a dot, our x squared plus 5 over 1 up 1 over 2 up 4, and of course the mirrored points we're going to look at. Now, of course, this is just a guide for pointing out what we're going to have. And we're coming through. And there's that part of that function. And of course, what we're looking at is for x being greater than or equal to 1. So we're looking at from this point on is the function actually that we're looking at. And let's get the other part of it. So we have 7 minus x, so we have x-intercept 7 over 1 down 1 over 1 down 1 over 1 down 1. And we have that nice straight line. Going through. And of course, it's part of it is we have, again, open dot. Let's actually do that in blue. So we have the open dot at that point, and of course anything less than. And so we're going in that direction along our curve. So there's our function, our blue and our red put together. And we're looking at, well, what is in our solution? Part B, we have g at 1, its function value. Well, its function value, of course, would be with that first part being equal to 1. So we would have, of course, 1 squared plus 5, or, of course, a value of 6. Now, of course, if we look at the limits in part C of this question, the limit of x approaching 1 from the negative side of our function g of x will actually be the limit of x approaching 1 from the negative side of 7 minus x, which of course, nice polynomial function, direct substitution in, 7 minus 1 giving us 6. On the other side, our limit of x approaching 1 from the positive side of our g of x, this of course gives us the limit of x approaching 1 from the positive side of x squared plus 5. Again, still a polynomial function, direct substitution. 1 squared is 1, plus 5 also being 6. So when we look at this and we put it together, we of course, therefore our limit does exist as x approaches 1 over our function g of x. It is actually 6. And what we can therefore conclude overall, that because g at 1 equals the limit of x approaching 1 of that function, g of x, because these two are equal, we can therefore say that g of x is continuous. Because we don't have that break, the possible change in our piecewise function actually joined together nicely. We didn't have a break, we didn't have that jump, and so therefore our function is actually continuous. Okay, let's move on to the next slide, and we can look through these to see if they are indeed continuous or not. So if we look at part A, nice part here of course, yes, it's continuous, and we're looking for, of course, continuous at the value of x equal to 2, right? So f of x is continuous. Let's mark that a little bit neater. And of course, this is a nice polynomial function, no breaks, and we're good to go. What about g of x? Well, g of x, which is x squared minus x minus 2 all over x minus 2, well, that breaks apart into x plus 1 times x minus 2 over x minus 2, which of course leaves us with x plus 1, but remember, x cannot equal 2. That's our whole, so therefore not continuous because of that whole at x equal to 2. Right? The function must be defined, and in this case, it's not. So let's scroll up a little bit. Part C, we have our function, so we have the same function as we did in part B, this being h of x, right, being our nice x plus 1, where x cannot equal 2. But what it's saying, of course, is that we have a second part to this function, that our value at x equal to 2 is indeed 3. So of course now the catch is our function defined? Is our limits defined? And so what we do, of course, is we look at the right and left hand limits. The limit of x approaching that value of 2 of h of x. Right? And now whether we go from the positive or negative side, we're going to use that first function. So they're going to be equal to each other because it's a nice polynomial function. That will actually be our limit of x approaching 2 of x plus 1, which of course direct substitution leads us to the value of 3. And so therefore our limit of x approaching 2 of our function h of x is equal to h at 2, because it's defined at that point, and therefore h of x is continuous. So they're throwing in the point where we had the hole in part B, they're filling it in part C, and it works out quite nicely. Looking at part D now, function capital F of x, and of course, we have a nice squared term. Now, of course, it's still not defined because of our whole at x equal to 2. Just because we have that nicely there, we still have a whole. So in part D, we have f of x equaling 1 over x minus 2 squared. We still have that. X cannot equal 2. It's not defined. It has a whole. And therefore not continuous. And let's look at part E. Let's scroll back a little bit. Part E, g of x, we have our 4 minus x squared, that is. And so let's take a look. We're going to have to look a little closer at it. So let's move it up a little bit. So in part E, we have capital G of x equaling our piecewise function 4 minus x squared and 3. And this is when x is less than 2 and x greater than or equal to 2. So the key point is where the transition is, because both of them are nice polynomial functions, so they'll be continuous at all points other than where they join. So what we're going to look at is the limit of x approaching 2, which is the point we focus on the question as well, from the positive and negative side. So let's start with the positive side of g of x. That will give me the limit of x approaching 2 from the positive side, where it's greater than 2 of our function. That of course gives us 3, which is just 3. The limit of x approaching 2 from the negative side of our function g of x will give us the limit of x approaching 2 from the negative. Well, from the negative side we have 4 minus x squared. Substituting in, nice polynomial function, we have 4 minus 4, which is 0, so we can stop right there. The limit doesn't exist, therefore not continuous, since the limit of x approaching 2 of our function g of x does not exist. Remember, it must exist and be equal to our function value. Okay, so there's a couple of quick examples on how they are continuous or not continuous. Lots of piecewise functions here, and as we get into higher levels of math, we'll have more and more of those. So let's try some questions on page 51, and this will wrap up our Unit 1. We'll have some review questions as well. We'll look to our outline to see what those review questions are and perhaps for our unit test.